This is the third part of the lecture, and my last one, as we said. I know I almost promised bringing pictures of the old days in what we call the Casa Lama. It's a house where we get together and drink and party until late, and then also be early here for the talks. But unfortunately, I didn't bring. I thought I had my external hard drive with me, where those pictures are, and I didn't. So I owe you that. So we saw the first two classes, basics of structured light. Then we saw a little bit of the basic of the interaction of structured light with atoms and with other media. And now we're going to get into the interaction not only with the internal degrees of freedom of single trapped ions, but also with the external. We will look at not only optical forces, but also resonant interactions against optical forces. And I will go by along different ideas and different applications and possible extensions of these fundamental tools that we have been developing over the years. Some ideas that we have already implemented, some ideas that others have looked into, and some that are still in the ink bottle. So again, a little review of what we saw yesterday and the day before. I'll try to go fast. So our object of study are trapped ions, as I will also be talking today. Only we're talking about one single trapped ion. Of course, these ideas can be extended and are extendable to more than one ion trapped in a trap. Those are the typical platforms that are used for quantum computing with ions, for studying quantum simulations, for studying, for example, heat transport or different effects using ions as a toy platform. I will not get into that, so what I'm again concentrating on is the basic interaction of structured light with atoms. And I will show you how we are starting to build some tools to do interesting physics with not only one atom, but more than one atom. Again, we saw that we have this kind of beams, the Gaussian beams, that are quantified by two indices, an index L and an index P. The index L accounts for this helical phase, which accounts for orbital angular momentum. We saw that these beams have a strong gradient in the middle, especially the L equal to 1 beam has a strong gradient, that there's an angular momentum associated with this phase, and that this angular momentum can be transferred not only to macroscopic particles, but also to the valence electron of a single atom, showing that actually in all possible scales, the orbital phase or the azimuthal phase accounts for an orbital angular momentum of a photon. So as said, now today we're going to look at what happens with the center of mass motion, and for that I will develop a little bit of the ideas of how we treat and how we work with ions and how we understand the motion of center of mass. But before that, a quick review. So we know that light can exert pressure on different kinds of material particles. As I already said, one of the oldest demonstrations of that was the observation by Kepler that the tails of comets don't point as the tails, I learned they're called the wake of a boat. So the tail, the wave that the boat leaves behind, but they point in the direction that the light is coming out from the sun. Mainly, it's a mixture of the two. And we know that for plane waves, this comes to like a plane wave that has, in a complex form this way, it actually has a momentum that is proportional to k and to h bar. And for structured beams, we can think like, okay, if this has a momentum that's proportional to this gradient, this thing now has a gradient that actually, well, here I just wrote rho, but it's rho divided omega. So we would expect to have a delta P because of this transverse gradient. Yeah? So we have these beams that have this transverse gradient here, and we expect to see some kick, some sideways kick. And I'll try to show you how we see such a transverse kick. So going back to the kind of setup that we have, this is a cenital view, so a top view of how we work on our ion traps, and this is a trapped ion. It's trapped through these electrodes, which are in yellow here, in some kind of almost harmonic trap. This 3D harmonic trap can be decomposed into 3 principal axes. And in this case, the setup was done in such a way where the beam impingement of the ion is coming with some projection on these 2 directions, which are the 2 directions that we call radial directions, and with 90 degrees, so orthonormal, no projection onto what we call the axia, so that would be the direction along this axis. This will be important in a second. What's important right now is to start to conceive that the movement of these ions in these traps correspond to the movement of a harmonic oscillator. It's a potential that is approximately quadratical, and for that we will then describe the motion of the ions in the trap. So the basic physics, the basic Hamiltonian, actually will be the James Cunningham Hamiltonian. We have, if from our ion, whatever it is, we single out 2 electronic energy levels, and we can think that we will treat those 2 electronic levels as a 2-level atom. So we just shine a laser that will be resonant with 2 of these levels. This will probably, if we are, for example, in a quadruple transition or a transition that we can drive coherently, this will behave like a 2-level atom that we can do quantum things on it. As said yesterday, the lifetimes are too short. This will still behave as a 2-level atom, but we won't be able to do quantum things. So we will choose a 2-level system where we can do quantum things. And on top of this, you have the center of mass, which the center of mass is the center of mass of a charged particle in the harmonic trap. So for that, we will have the dynamics of the harmonic oscillator. The Hamiltonian of this is nothing else but just a part for the electronics, so just a part that has a 2-level system and a continuous variable system with a harmonic potential. Typically, because of the masses and the frequencies that are used in atomic trap ions, the frequency of the trap is much smaller than the electronic frequency. It can be either 10 or 100 times smaller, or it can be something like 10 to the 6 times smaller, depending on what you choose as a 2-level atom. So you can think of the energy level diagram of this coupled system in what is called the ladder representation, where you have in this direction you put the n state, so n minus 1, n plus 1, and in this direction all the way to 0. And on the top and the bottom you etiquette the excited electronic state and the ground state. So that's just the free non-interacting Hamiltonian of these 2 systems, which in principle are pretty decoupled. If you don't do anything, there's no coupling between these 2, almost no coupling between these 2 things, and the system will evolve as just 2 totally independent systems. But of course, fortunately, we can actually, using laser light, couple these 2 things, and that's where we will build the James Cunningham Hamiltonian. I won't go into the exact detail of all of it, but I will just go through it. If you'd like to look at it, that's written in many books. There's one I like a lot. You can write this on the slides, which is the book by Steck. I'll write it down on the slides and I'll update it on the link if you want later. But the thing goes like this. So we want some light-matter interaction. Light-matter interaction can be either of the dipole type, depending if it's a dipole transition, or of a quadrupole type, or it can be magnetic dipole, whatever it is. But whatever it is, the Hamiltonian will always, in the end, look like something. The interaction Hamiltonian will always end up looking like something like this. Something that has something that we call the Rabi frequency, which is a number that quantifies the intensity of the interaction. So that has geometrical things of the atom, it has polarization of the beam inside, it has orbital coefficients, it has amplitude of the field. All of that information is basically summarized in one number, which we call the Rabi frequency. And then you have the operator that basically, if you look at the dipole case, it would be the D operator, which is the X operator, which is we can either excite or de-excite the state. So you compose this X in excitation, and then you have the part of the electric field that you have the traveling wave. Of course, you can have a standing wave, and this will change a bit, or you can have a structured field, and the shape of this will change a bit. But you basically will have a function which will be a function of the coordinates and time, something like that. So we will concentrate on this for a second. The typical thing to do for treating this Hamiltonian, which is not absolutely necessary, but it gives you very clear equations, is what's called the rotating wave approximation, and you go to what's called the interaction picture, where you play a little bit with this Hamiltonian, throw away high frequency terms, keep on the main important terms, and you end up having something that looks really like this. So you have a term that has a raising operator for the electronic levels. This term, which basically is e to the, so it comes from the kx here. Yeah, so we have this parameter beta, which I will define in a second, down here, and then you have the x coordinate here, so that's the quantum harmonic oscillator x coordinate. Then you have the detuning, and of course you have the Hermitian conjugate on the other side. This parameter here is called the Lamtic parameter. It basically comes from this term here, and the fact that you're integrating over a region where the ion is. So basically the Lamtic parameter is k times the spread of the zero wave bucket, so the spread of the zero wave bucket divided by lambda, and it basically tells you how big the spread of the ion is with respect to your wavelengths, your laser wavelength. Typically for trapped ions, this parameter is somehow small-ish, not totally small, but smallish that you can do a Taylor approximation to see what happens term to term. And if you do that, the first term is what we call the carrier term. The first term just has sigma plus, sigma minus. And that would be transitions which are indicated here, just like transitions from, without changing the vibrational number, so the N number, the harmonic oscillator number does not change. Of course, you can also do here or here, but here are the arrows indicated whether you just start on NG. And then you have other terms which are called the red sideband and the blue sideband, which are the next term in this expansion, where they are scaled by the parameter eta, and you have the combination of an excitation and a de-excitation and a de-excitation with an excitation. So that's what we call the red sideband, which basically gets you from a state which is in the ground state, it gets you excited, but you lower your vibrational number on 1, or the other term that actually goes in the other direction. And these terms can be singled out by frequency. So what's not written here, it's a little bit under the carpet, is that these terms have oscillating terms, and they will only be present and big whenever your laser is tuned to exactly this difference of energy, or this difference of energy, or this difference of energy. Of course, if you are detuned, there will be some interaction, but it's a detuned interaction. At first order, you can leave that out. So you can basically say, like, by tuning your laser, that's again not right here, but by tuning your laser, you can tune to having this kind of interaction, this kind of interaction, this kind of interaction. And this has been the basis of ion trapping as a quantum processor, as a quantum device, because it basically allows you to not only, for example, cool, if you want to do, if you're doing steps like that, you can cool your ions. You can also move excitations from the electronic part to the motional, and like this you can actually make, in a way, two ions that are trapped interact through what we call like the motional bus. So you use the movement, the common movement of trapped ions to make their electronic parts interact. I won't get into that. I will just show you how these things look like. So if you look at the spectrum, this is a spectrum of a quadruple transition. So this is the laser frequency. This is the excitation that you see. And you see, for example, if you start scanning, you see horrible things like that. Lots of peaks, some very, very big peaks, and some other peaks that are a little bit smaller on the side. And if you move your magnetic field up and down, and you start to identify, okay, I see one peak, this moves up and down, and so you start to realize, okay, this peak looks like it's a transition from the S1/2, M minus 1/2 to D, I should say D 5/2 here, that's wrong, M minus 1/2, and you can identify all of these big transitions as the carrier. They're bigger. Why are they bigger? You see this one has, all of these ones have eta multiplying. Eta is normally a number that's smaller than 1. So you first identify these ones, and then if you zoom and reduce your power and you look around this one, you see that you have your main peak, and to the sides you always have peaks to one side or the other, which are symmetrical. This here is another measurement done in another lab of a very similar experiment, where you see your carrier, this is the center peak, and to the sides you see the axial peaks and the radial peaks, and they have different frequencies. So these are the three different frequencies, the three different motional frequencies that your one single ion has. Of course, if you have more ions, we'll have more modes, this will become a mess. The spectrum will become very complicated, but still understandable. Good. So, and what is actually happening when we are actually tuning the laser to this axial sideband? What we're doing is we are giving the motion of the ion an extra. We're here with the red. We're actually subtracting a phonon, and when we're tuning to the blue, we're actually adding a phonon. So the transitions that we're doing are actually this kind of transition. So you're doing this transition where you're adding a phonon apart from getting excited, or you're subtracting, whether you're on one side or the other. And actually, this is curious. You see the height of these two are different. The height of these two are different because the population of the modes is low enough so that you actually can tell that there is a symmetry between going up or down, because you know, when this A or A data acts on the number on the number state, it will take out a square root of n or square root of n minus 1 or plus 1. So this plus 1 or minus 1 makes the one bigger or smaller, whether you're going to the blue or the red, if n is sufficiently small. And you can actually tell the temperature of the ions by the asymmetry of these two peaks. So, how does the experiment that we did with the Gaussian beam work? So we started in a situation, and I will go very slowly through this class. So this is again the same kind of spectrum that you see here. This is the spectrum here, where you see all of the possible sidebands. So the axial and the two radial ones. In this case, we, as I said, our configuration is written again as a reminder in a very special way, where the k vector does not have any projection along the axial direction. And when we do that, when we shine a Gaussian beam centered on the ion, if we look at the spectrum, what we see is that the carrier is very big, as expected. The two radial modes in the blue and in the red are there, but the axial modes are inexistent. And this is pretty reasonable. What basically this is telling us, and that's what's the information that gets captured in that Rabi frequency, in the geometry of the state, is that you cannot, with a beam that's going in this direction, you cannot push an atom transversely, normally. So if the beam is just a traveling wave, it will just have a gradient in the longitudinal direction, so it can only push things in the longitudinal direction. As you see, the two radial directions have projection to 2K, but the axial doesn't. What happens if we switch to a vortex beam? We switch to a vortex beam, and now there's a transverse gradient. There's a transverse gradient, and what happens? The axial sidebands turn on. You see the two axial sidebands turning on here. The carrier reduces a lot. Why does the carrier reduce a lot? Because in this particular situation, the ion was not made to be sensitive to the gradient, so this should actually completely turn off, but it doesn't completely turn off because the ion, again, is a wave packet, so it somehow senses a little bit of the intensity on the sides. And well, the radials also have some projection onto a transverse beam, because this beam also has a gradient in the vertical direction, so the radials are still there. So this was the first nice demonstration that we can actually push ions sideways with a beam that's going forward, which was kind of nice. And just to understand a little bit what's going on here, so we were going back to this scheme. We chose the polarization in such a way that the electronic transition that we were doing was from -1/2 to -3/2. Yeah. So in principle, this electronic transition has to be, consumes, let's say, one quanta of angular momentum. And we still have the other quanta of angular momentum extra, which is due to the orbital part, and that's what allows us to now do this transition that was forbidden before, which is changing the center of mass motion. A little bit into going back, I will go quickly through this, not to bore you, but as I said, the derivation that I went quickly through of the James Hamiltonian was a derivation for the dipole term. If you do it for the quadruple interaction term actually looks like this, so it has a gradient of the field with respect to the coordinates multiplied by the coordinates squared. And if you look at this term for a traveling wave, well, what you get is this, from this gradient, you get a k there, and then you get the exponential of e to the I k z. So that's something that actually will push you in the z direction. But if you do the same thing for a transverse orbital momentum beam, which has this kind of shape, the electric field, then you will see that you still have this term. But on top of this term, you have an x and a y term, which are linear, which appear linearly, which basically account for this transverse gradient. So basically, what we see is that in principle, the carrier term, the term with so the first term here, when you expand this, is a 1, and the next term is the kz. So that's a strong carrier and a weaker sidebands. But in this case, the sidebands are in principle stronger than the carrier, because the first term is actually a term which is linear on the center of mass coordinates. Good. Another thing that's just so things that we measured, we actually could measure. So this is the Lambda parameter for that we can measure. So the Lambda parameter in this case is not x over lambda, but x over the waist. And for different laser powers, we measured that this Lambda parameter was very much where it had to be. And that's about it. So we did this with quadruple tuned, so vortices that were tuned to quadruple transitions. And an interesting thing that one can think of is that you can actually do what we call radially address action gates. I will tell you in a second what that. I will tell you now what that is. And you can think of using this for thermometry of planar ion crystals. So what's the idea? I will go to the board. So imagine you have an ion crystal that has many ions like that, blah, 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 blah. And you want to know, you want to focus lasers on each of this one or the other one to have information about the movement or about the state of each of these ones. Or if you want to make, for example, this one here interact with this one here, you want to shine a laser on this one and on this one and not on the other one. So the best thing you can do for that is come with a laser which is perpendicular to the ion chain. The thing is that if you do that, you only have access to the information of the movement in this direction. And that is a little bit complicated because the radial modes suffer from something that's called spectral mode crowding, which is all of the modes get together. I showed you the picture of all of the modes, how the spectrum looks like a mess. So when you have many ions, it starts to be difficult to identify them spectrally. So a nice thing that happens that you can use with this thing is that coming with lasers that are in this direction, you actually can get information about the movement of the ions in this direction. So you can actually impinge forces in the transverse direction, which are very useful if you want to do gates or to thermometry. But in the future, and actually this is part of Corina's project, which we are working in collaboration with the people in MINDS, we actually want to move not only structured beams, not only for quadruple transitions, but for what we call dipole tuned vortices, which are basically Raman transitions. And there are two different things that you can do. So you can be very detuned and you will have conservative forces. I will talk a little bit about that in a second. And you can also be a little bit more resonant and have some coherent, incoherent interactions, which I'll also tell you a little bit about the first steps that we did there. So, but before turning into that, we go into part 3, which is what we call optical forces. So I will tell you a little bit about stark shift and spin-dependent forces. So the kind of forces, in the sense that I've just showed you, or movements, are not really forces in the sense that the kind of motion that one imparts onto an ion is phonon by phonon. And a phonon is not, so exciting with a phonon, a harmonic oscillator, is not really the same as putting a force. So you know, the phonon modes are all, they're not oscillating in one direction or the other one, you're actually putting a force that goes in one direction or the other one. At the same time, you're changing the quantum statistics and you're imparting energy, but you're not really imparting a force. To impart a force, you need to impart forces. So not only resonantly interact on given transitions, but really be able to coherently move the center of mass of an atom. And the way to do that normally is by off-resonant lasers, and I'll tell you a little bit about the physics of that. Okay, this slide is a little bit of a mess when you first see it. Should have cut it a bit. But think of it, let's think of our two-level systems. We have a two-level system, a ground state and an excited state. Forget about the motion for now. And you have a laser that is tuned, not exactly to a transition, but they're tuned by a given amount. When you go through the optical block equations or solving the Hamiltonian of this open system, you find, okay, you have again the frequency of your excited state, the frequency of your ground state, and an interaction Hamiltonian that looks exactly the same as I wrote before, now written as sigma x times an oscillating term. Again, you can go to a rotating frame by doing this transformation, u equal to sigma z, so like, going to a frequency that's rotating with a given frequency, but between these two states. And what you find is that your effective Hamiltonian then looks something like this. A new renormalized Rabi frequency, and a rotation around z, and a rotation around x. If you say, okay, what happens if I'm very detuned? So if the detuning is much bigger than the Rabi frequency, so this detuning in frequency is much bigger than the frequency that will go up and down, then this Hamiltonian actually reduces to the following thing here, that when you transform back, actually your Hamiltonian looks like the original Hamiltonian, which is sigma z times the frequency of the difference of the levels, plus something that depends on the laser intensity, on the interaction of the atom with the laser, divided the detuning. And you see, this is a shift. So you basically, by shining a laser which is very detuned with respect to a frequency, you change the energy levels of your atoms. So that's the basic idea of what we call the AC stark shift, or the Outler-Towns effect. The Outler-Towns effect was the name it had when people were looking at these things in the microwave regime and in the era of the maser. But now in optical regime, for some reason, people have decided to change its name to AC stark shift. Anyhow, so why is it an AC stark shift? So basically the energy levels get shifted, as I do here, in a very untidy way, but also kind of cute, I would say. And so your energy levels first were separated by omega A, and now they're separated by a given amount, which is omega A plus this amount, which is here. So what happens when you have this kind of things? Or where can you have this kind of things? Well, you can have this kind of things in many different places. But one curious thing that happens that we first looked at is the following. So when you're driving this quadrupole transition, so you're shining a laser here at 729 nanometers, which basically drives transitions from the S to the T state. And this laser, you put it very resonant. So there's no AC stark shift on this transition. But of course, your atom has many other transitions, like for example, this D to P, this D to P, and so on and so forth. And if you look at the wavelengths of this transition, this is 854, 866. These are transitions which are dipole transitions, which are transitions that get excited very easily. And they're not so far away from this wavelength. So what happens when you shine this laser on this transition, actually this energy level here, what reduces a little bit because of the stark shift between this level and the top level there. And if you want to use this transition, for example, as a clock or as a frequency reference, or you want it to be stable, independent of the power that you put on this beam, that becomes a problem. So the first thing that actually we showed the first time we managed to do interaction with atoms in a hollow beam was that if you did interactions in the center of the hollow beam, you can reduce the AC star shift by a factor of around 40, which is very nice. So you can actually drive transitions here, and you reduce this AC star shift 40 times. And we thought this was nice for clocks. And some people followed our idea, and they actually, this paper that came later, so excitation of an electron-optical transition by twisted light. They basically showed that, I won't go into the details of these graphs, but they basically showed that in this case, they were deriving not a quadruple transition, but an octuple transition in Eternium, a transition that is actually used and actually has one of the best records for optical clocks. They showed that they reduced the AC star shift, which is one of the biggest problems in this transition, by 4 times. They were not as good as the result that we had, probably because they didn't have so good focusing, probably because the ion was not so well contained, but anyhow, they showed a reduction. Being the devil's advocate, actually in the meantime where we were thinking these things, people developed some techniques which don't rely on focusing on very tight beams, which is called hyper-Ramsay spectroscopy, and you can get totally rid of AC star shift doing this. So this hyper-Ramsay spectroscopy is an extension of the technique which you probably read about, and I think you talked about this morning, which is the spin echo. So the spin echo is a technique to get rid of magnetic fields or whatever field you have which is constant during your operation, and these things where you just use 3 pulses, and hyper-Ramsay spectroscopy you can use 5, 6, 7 different ways of doing it, and you can actually reduce the AC star shift by 2 to 4 orders of magnitude. So really for clocks this is something. So this is a best way than actually using this reduction of the AC star shift. Good. There's another point where people are looking at using these hollow beams for reducing AC star shift. So not in the realm of ion trapping, but in the realm of atom trapping, which has become very hot over the last years, because people have demonstrated actually the most powerful quantum computers in terms of this very nice measure, which is quantum volume. Nowadays are trapped atom quantum computers, where the interactions between these trapped atoms that are trapped in the array are done via Rydberg interactions. One of the problems with trapping atoms is that you're trapping it with a strong field, and that moves your energy levels. But there was a beautiful technique discovered which basically allows this thing, which is the idea of what's called a magic wavelength. Beautiful name, by the way. So the idea of the magic wavelength is, so if you, let's say, this laser is the tool with respect to that transition in a given amount, and this laser and it's also the tool with respect to this transition or this other transition in a given amount, and sometimes it will push the levels up, and sometimes it will push the levels down. And there's a given frequency where, for example, here it's pushing one up and the other down, where the push that it does on the 2 levels, so it's a given specific wavelength where the push that it does on the 2 levels is exactly the same. So you're in principle insensitive, so those levels won't shift with respect to. So this works well. But people are still anyhow looking into doing traps of atoms where they're actually trapped not in the bright part but in the dark part of things, so using not instead of bright spots for trapping, but orbital angular momentum beams or vortex beams, where the atom gets trapped in the hollow part, and you reduce these fluctuations even more. So, I told you I was going to talk to you about forces, so I will now talk to you about forces. So, as I said, you have, when you shine a laser that's the tool with respect to a transition, you have a shift in the energy levels. And now imagine you have 2 beams counter-propagating, like one beam coming from here and another coming from there. If you do that, you will have a standing wave, so not the traveling wave anymore. So you will have regions where you have very strong electric fields oscillating positively and negative, and regions where the electric fields are on average very low. So you will feel in principle a force depending on your spin state in one direction or the other one in these spatially structured beams. And this has been known and has been used actually for a long time. And this was the basis actually of explaining the first Doppler pooling experiments it's a kind of crazy nice anecdote. When people started doing Doppler pooling of gases, they found out that the temperature they were reaching were like 100 times colder than what they were expected by the theory they had. And Claude Contanucci, who you might know because of his very famous books on quantum mechanics, came up with an effect which he called the Sisyphus effect, which uses this idea of optical forces on a standing wave to explain why you actually cool to much lower temperatures, and that's why he got the Nobel Prize for. So I won't tell you about optical forces with structured light beams, which is the direction in which we are trying to go in research in the future, but I will tell you a little bit about these optical forces and what you can do with it and what you can do with ions. Mainly because I did a couple of things which are nice in this realm, because other people did some of the most beautiful experiments that I like in quantum mechanics with trapped ions, and also because I think it's instructive. So the idea is the following. You have first a very big harmonic potential in which you have one single atom and you shine, and counter-propagating beams will generate an optical potential that looks something like this. This will generate a star shift that will look more or less like this potential if you would have a two-level atom. Of course, you don't have a two-level atom, you have an atom that's a little bit more complicated. So normally, or sometimes, the simplest thing after the two-level atom is the four-level atom, where your ground state is an S1/2 state, so you just have the spin on this state, and your exciting state is your P1/2 state, so you just have, so of course, because of the coupling of L and S, you can have P1/2 or P3/2. Normally these things are separated enough in frequency, but this is the simplest, so for optical fields. You can have probably things a little bit simpler if you look into magnetic transitions. But anyhow, and then here you have sigma plus transitions, sigma minus transitions, and pi transitions. So depending on the polarization of your beam, you will be exciting these different transitions, and these different levels will shift differently depending on the polarization of the beam that you generate. And this kind of beam, so if you shine a beam that has vertical polarization in one direction and vertical polarization in the other direction, it happens to be that you generate what is known as the limb per limb configuration. Why is it called like that? Because the polarization somehow shifts from being linear to being circular, to being perpendicular, to being circular, then linear again, and then perpendicular. So the polarization shifts along the beam, but basically what you see is that so that's in all cases, so when you have linear polarization, on this state, these two states are shifted the same. So the places where you have linear polarization, you have no change of energy. And the places where you have circular left polarization, that's sigma minus, you will have a shift on this state, and the place where you have sigma plus, you will have a shift on this other state. So basically this optical lattice or this optical interference pattern looks like like a potential for the different spin states, which are actually dephased one with respect to each other. So you can actually push one of these ones, so if you put an atom, for example, with this spin state here, this would be in a minimum, but if you put it here, it would be in a maximum, and it will try to fall down here, and the opposite for the other spin states. So we put it here, we put it over here, yeah. And you can use this optical lattices either to trap atoms in these valleys, or actually to impart forces on them. And you can do it either statically, just by placing an atom here and letting it fall, or you can do it dynamically by using what is called a standing traveling wave. It's an oxymoron that I love. So what's the idea of a standing traveling wave? So you have your two beams coming in one direction or the other one. If you detune one of them a little bit with respect to the other one, say you detune it 5 megahertz, 2 megahertz a bit, so your interference pattern will be moving at that frequency in one direction, which is 5 megahertz with respect to optical transitions is very, very far away. Optical transitions are in the hundreds of terahertz. But if the speed at which these bumps pass the ion are resonant with the motional frequency of the ion, which is normally around 1 megahertz, you can resonantly excite motion of the ion. So that's why it's called the... So it's standing because with respect to the frequency or the speed of light is very slow, but it's actually moving at some velocity. And if you make it move at a velocity such that you hit the trap frequency, you can resonantly excite movement of the ions in an oscillatory fashion or in a constant direction, one direction or the other one. So you can, either if you put it exactly in resonance or a little bit out of resonance, you can actually excite any kind of motion of the trapped ions. How do you do that? So normally, this is a very pictorial view of how this thing happens. So you come with a beam that you separate, you send them through acousto-optical modulators that allow you to shift the frequency. So one will be shifted by omega, the other one by omega plus the trap frequency. So they will differ in the trap frequency, and this will generate a traveling wave over the ion. This magnifying glass is the ion chamber. Now it has been simplified to that. And you can generate motion like that. And if you look at what happens in phase space, so phase space you have the x-coordinate and the p-coordinate. If you have a resonant drive, what will happen, of course, well, you will start to acquire more amplitude and you will oscillate. But if you are a little bit detuned, of course, what will happen, you will start to acquire more amplitude, and at some point your phase will shift and you will come back here. After you do that, you will accumulate a phase, and actually this phase accumulation is the basis for gates with trapped ions like this. And you can also look at this in a rotating frame, so instead of having a spiral in a rotating frame, what happens in the resonant drive is you just acquire momentum or position, whatever you want, and the detuned drive is something that just goes out and goes in. And what happens with this, with this state, is an interesting thing that, as I told you, as the wave has different, if you place here an atom with spin up, it will go in this direction, but if it has spin down, it will go in the other direction. What happens if you have an atom that you place and you start with a drive like this? Well, what will happen is that the spin up will go in one direction and the spin down will go in the other direction. And this is exactly a cat state. An atom which, depending on the internal spin, it will go either into big P or small p, so alive or dead, or the other way around as you want it. So here our macroscopic state, which is alive or dead, is the momentum or the position, which drawn here. Why does this curve like that? Because I'm thinking that you have a slightly detuned drive. And this was actually used, so this result was first shown by Monroe and Wineland and other people in 1996, where they did exactly something like this. So they first start with one of the spin states, then they create a superposition of the two of the spin states. In this case, they first did a kick on just one of the spin states, then they inverted, and they did a kick on the other of the spin states, and that basically made them their cats, making this, depending on the spin, going in one direction or the other one. And what we did with this thing was something kind of curious that we started doing because we were interested in what we call phase locking these kicks. And to do that, we combined doing electrical kicks, so moving the voltage of one electrode, which actually moves the ion in one direction or the other, with optical kicks. And we saw that if we did, for example, so if we started with spin up, we first did a kick in one direction. And if we started with spin down, the optical lattice did a kick in the other direction. And then by doing a second kick, which was always electrical, so it's always in the same direction, that leaves you in a different place in space, and it leaves you with a different excitation, which is which goes counterclockwise in one case and the other one. So if you wait for this phase, and you see that actually we could kick one ion in one direction and the other one in the other direction. So this is a measure of the displacement amplitude given this phase. And you see when this phase is zero, for example, in the red case you have zero excitation, but in the blue case you have maximum excitation. So we basically showed that we can actually do kicks that are phase reference to the macroscopic track. And we then later used this for a very nice experiment, which came published in PRL, which was had this title, a spin heat engine coupled to a harmonic oscillator flywheel. So this is an auto engine, where what we did is, so the ion was placed exactly in this place where it sees, depending on the spin state, so if it's in the blue spin state, you will see a potential like that. If it's in the red spin or orange spin state, you will see a potential like that. And we changed the effective temperature of the ion by optical pumping, and then the ion got compressed or decompressed because of the movement in the optical potential. And we showed that we can actually drive a thermal engine of a single ion, that the spin was doing like the work mechanism, it's what was being compressed and decompressed because it was moving in the optical potential, and the motion of the ion was what actually was accumulating this thermal energy. So the spin got pumped to either this polarization or this polarization, so more polarized in one direction and more polarized in the other direction, while it was, so this is how the experiment went. So you first cool down, you initialize your atom, you do some optical pumping to the given state, and then you alternate the temperatures, so by alternating the spin polarizations, and at the same time you apply an optical Doppler force. And at the end, you apply a sequence of pulses which allows you to analyze what the final movement of the atom is. And what you see is, so these four graphs here are the reconstruction of the Wigner function as a function of time of the operation of the engine, and you basically see first you have cold atom with almost no movement in the wave packet in the center, and as the time goes by, this thing starts to rotate and accumulate energy, which is somehow what we call the flywheel. The flywheel is, in any motor, in any real motor, you have the pump, and then you have the wheel, which is what's accumulating energy, and here is the flywheel. It's not exactly a flywheel because it's not a rotor like in a normal engine, but it's a harmonic oscillator that starts to oscillate around its potential limit. So, that's it for optical forces, and I will switch on to the last topic of today, and I will now go away of quadrupole and Raman transitions, and I will go into more simple things, but also pretty nice. So there's another effect that is sensitive to the gradient, which is what we want if we want to see things that have to do with structured beams. And that effect, so I first said there's the momentum transfer, but there's the counter of that effect, which is the Doppler shift. So, and what we actually showed, and gave it this funny title, was just rotating ambulances. We showed something that we call the rotational Doppler effect. Actually, our work was inspired, it has a very Latin American inspiration. The first measurement of something similar to this was done in Recife by Tabosa's group. That's wrong what I said. It was done in the Samas group in Uruguay, but the proposal came from people from Recife, from Tabosa and Madrid. And this is one of the first, or one of the important experiments that came out from the lab in Buenos Aires that was done by Nico and Muriel, who are not here. Muriel was here at the last edition of this school, with Marcia and Cecilia. Cecilia is also an ex-student of the school. So what's the idea? So normally Doppler effect, you can sense something that's moving towards you or away from you. If something is moving transversely against you, you don't see that effect. Of course, in ambulance, if you step a little bit away, it's still somehow moving towards you and then away, but the farther you go, the less you feel the Doppler effect. And if actually an emitter is far away from you and just rotating, you will not feel any Doppler effect. Unless you use structured beams, and that's what I want to convince you today. So the Doppler effect is everywhere, right? The Doppler effect has been used to study and determine in astronomy the movement of stars, and from there determine that they actually have exoplanets. It allows us to determine the age of the universe and different parts of the galaxy. It allows us to sense the temperature of gases by looking at the broadening of lines, and it allows us to cool and contain gases, quantum gases in different combinations. It has allowed the last 30 years of development of atomic physics and the construction of, from optical clocks to the prototype quantum computers. But what do we know? So from the standard Doppler effect, you have a wave traveling, and you have something that you're going to measure, that's an atom that's moving at a given velocity with respect to a wave. And we've all learned in either high school or first year in university that the way you can calculate the change in the frequency is by counting how fast you pass this wave fronts, this given waves, and you get to the result that the frequency that the atom sees with respect to the frequency of the laboratory is shifted by 2 pi over lambda times the velocity. And this is what you call the Doppler shift. But what you're actually seeing here is that what you're doing is you're counting wave fronts. And a spiral beam has spiraling wave fronts. So how do you actually count wave fronts? The way you actually count mathematically wave fronts is looking at the gradient of the field with respect to the modulus of the field. So this is actually a way to mathematically count wave fronts. So you can write this in a specific, generally like that. And your Doppler shift in general then of any electric field will be then the gradient of the field divided the modulus times the velocity. If you do that for a linear Gaussian beam, you get this horrible expression down here. So you have lots of Doppler shift. But there are a couple of things that you can probably identify, and there are 2 that I want to concentrate on. So you have this first big term, which ends up multiplied by the velocity in the z direction, that's the direction of propagation. And you can identify this k here, k times v, that's the planar wave Doppler shift. All of the other things, there's things that have to do with the curvature, the Q effect that I mentioned. And then there are 2 other things that appear here. There's another Doppler shift that's in the radial direction. And then there's this very funny part here, which is proportional to L, and that's the one I want to concentrate on now. Because it's an azimuthal Doppler shift. You see, you actually sense the velocity of something moving transverse, but azimuthally with respect to the beam. And it has another peculiarity, which is it has no length scale. You see, all of this has k, this has ZR, which is the Rayleigh range, this has k. But you see here, there's no length scale. So, in principle, this effect doesn't depend on the size of the beam, doesn't depend on the wavelength, and it diverges with respect as you get closer and closer and closer. Yeah, of course, what you have is, so you have the center of your beam, and basically what you're saying is that so you have to go 2 pi around this thing, and the closest you go, so if you go around on a big circle, of course, you have your gradient takes this radius as the length scale, but if you go around here, then your phase is changing very, very fast. And it diverges as you go to the center. This divergence is not really a problem because also the intensity of the light goes to 0, so you don't get a real divergence problem. But it's something that actually starts to go up. Why is it not a divergence problem? Because at some point you have the size of your atom here, and then that's as small as you can get. Because then when you're at the size of your atom, you're pulling your atom from one side and the other one, and then you don't see this effect of just a push in one direction. Good. So we're going to try to observe this thing. And to try to observe this thing, the best thing we can do is to try to get rid of all of this crap. How do you get rid of a lot of terms in Doppler shift in atomic spectroscopy? So there are 2 tricks that are very well known, or 1 trick that is very well known, and it's 2 photon transitions. And there are probably many types of photon transitions, but the most common one are the following 2. So you have a ground level and you have an excited level, and you basically choose your excitation field such that the frequency of the first field and the second field match the frequency of the total atomic transition. If you actually choose each of them to be exactly half of what you need, then, and you put them in a configuration such that one goes in this direction and the other goes in this direction, you can intuitively see what happens. So if the ion is moving in this direction, it will see this one blue detune and it will see this one red detune. But in total, it will see the total energy from the two photons will be the same. There's another possibility, which is doing Raman or Raman transitions, where you go from a ground state close to an excited state. Normally you have some detuning here, and then you go back to a groundish level, or a level which is, again, at a lower energy as the excited state. And in this case, you are not absorbing two photons, but you are absorbing one and you are emitting the other one. So in this case, to have zero detuning, so zero Doppler shift, you need to come with both lasers in one same direction, because you are absorbing one and you are emitting in the other direction. And this configuration is not only used for this kind of what's called Raman transition, but also what is known as CPT, or which is coherent population trapping, or EIT transitions. And I will show you a little bit more about that in a second. But, so what happens? So if you take this Doppler shift or the Gaussian beam, and you look at the configuration, which we will concentrate in such a configuration right now, and you shine two lasers like that, the two of this very similar energy, and you basically look at what happens with the Doppler shift, all of these terms cancel, and you basically have that the ending Doppler shift that you have is just the difference between the L of one of the beams with respect to the L of the other of the beams divided by R times the azimuth velocity. So if you have two beams, and this is the idea, you have two beams superimposed and they're counter-rotating, so there's here one double beam rotating like that and the other one rotating in the other direction, then in principle, as they have opposite they have opposite angular momentum, they will cancel. But if your beams are co-rotating, then they will add together and you will see this Doppler shift. This is the other way around. Yeah. I was saying it, I can say it wrong. So the formula is okay. If they're counter-rotating, so what's wrong is what's down here, right? If they're counter-rotating, of course, one beam is going like that, the other one goes the other direction. So you see the shift if they're counter-rotating. No, now I'm saying it wrong. So when your beams are exactly equal, and they're both in the same direction, yeah, that's when you have no shift. Yeah, this is the other way around down here, sorry, I missed that. Anyhow, of course, you need to have the same L here and here, and then that does it. Cos for, yeah. Good. So, where do we see these transitions? We look at these transitions in calcium, sorry for that slight mishap. So, this is our energy levels, and if you shine these lasers, the blue laser in this transition and a couple of red lasers in this transition, we actually shine two of them here, you see that your absorption spectrum of the UV looks like this. It has a big absorption curve that corresponds to the normal absorption of this transition, but it also has this very strong dips. This here is a simulation right now, I'll show you data in a second, which come to be what we call dark resonance. So at some point the fluorescence drops, and that's because you actually generate a superposition of these states, or of this state and this state in this case, and of these states in this case, which are not excited by the electric field. This effect is called dark resonances or coherent population trapping, and it's a version of, like a semi-incoherent version of what I was showing you as Raman transitions. So for what follows, we will concentrate on this kind of transitions where the two beams have almost the same frequency. And what happens, so if you shine with two laser beams, which are co-propagating, you will see that the Doppler shift, and they're Gaussian beams, you will see that the Doppler shift totally cancels out, and you see this dip, so this is just a schematic of one dip, These are the two dips that we actually see, and you see these dips are very, very thin. These dips are as thin as the coherence of these states can be, and they're only broadened by power broadening or by the coherence broadening. But they can be, as you see here, we got them thin as 10 kilohertz. So this is a very sharp, coherent effect of the interaction of these two levels with these two laser fields. What would happen if you would have a slight angle between the two of them? So if you would have a slight angle between the two of them, of course now your Doppler shift will be proportional to the velocity in the difference, so it will be proportional to the velocity, the transverse velocity to these two beams that are at an angle. And how will you see that? So if you look at your spectrum, and you have, if your velocity is given by a mean velocity because of a thermal distribution, you will see that your dip gets shallower and shallower as you increase the temperature. So here the temperature is given as a line broadening, but as you increase the temperature, so this is colder, hotter and hotter, your dip will be shallower and shallower. Or alternatively, what you have is driven motion, which in traps you have a kind of motion that's called micromotion, where your ion oscillates at a given frequency. Your original peak will now show sidebands to the side, so you will actually have a modulated spectrum because of this harmonic motion. But in any case, whenever you have motion, you will see that your peak gets shallower. If you just look at your peak, you will see your peak gets shallower. So this is what we did. Now instead of opening up the two beams, what we did is we put them collinear, and we put them in such a way where, this is hard now. We put them in such a way where we could actually put the two beams co-rotated or counter-rotated, and we looked at these peaks, and we saw that when they're co-rotating, so the two beams are exactly the same, the dip actually goes very low, and when they're counter-rotating, the dip actually goes not so low, showing that it's sensitive to some kind of motion. We characterize that motion. We know that it's transverse motion of the trap, and it's transverse micromotion. We actually could see also the echoes that are not showing here, but this already shows that we are actually sensitive. So when the two beams are perfectly co-propagating, you still see motion when you make them co-rotate. How did we make sure that everything was okay, and how did this experiment actually happen? So this experiment happens with one trapped ion and a couple of beams that come. It's first a beam that comes, a single beam that goes through a faceplate that transforms it into like a Gaussian beam, then it gets split into two polarizations, and then it gets recombined here. And what we do is, I'm trying to see, I was asked the other day what happened with so this is just one, so this is not two photons, so it's recombination, so there's no two photon interference. But of course, if you want the beams to recombine with the same, so with the same or with opposite rotations, you can add an extra reflection, and by adding an extra reflection, you can do it so if you have just a mirror, you will have just one reflection, or if you add two mirrors, or we use something called the Duff prism, which just automatically does two reflections like that. It's nice and easy to align. You will invert the sign of your beam type, and effectively produce either co-rotating beams or counter-rotating beams. And that's the result that I showed you before. So in purple, you see the co-rotating case where you're insensitive to motion, and in orange, you see the counter-rotating case where you're sensitive to motion. We also tried something which was just to see if there was no problem with the misalignment of the beams, if they were not perfectly aligned with respect to each other, because we separated them and we realigned them together the best we could. But, we on purpose misaligned them, and you see, if you on purpose misalign them such that the two lobes match, like here, you actually get the opposite effect, because of course the face, in this case when they're counter-rotating, the face here for the two of them is the same. It's like it's a phase of the two going in the same direction, so again you're insensitive to motion. But in this case, although they're co-rotating, the phase in this, that the ion sees in this misaligned case corresponds to phases that are going in different directions, so you're again sensitive to motion. And that shows that the effect that we're seeing is not a misalignment effect, so it's robust to misalignment, and it only depends on if the phase is going in one direction or the other. But what we were interested in seeing is the dependence. So what happens when you move your ion across the beam? And this is what I'll explain this graph in a second. So as we go through, so this axis here is the position of the ion across the beam. What you see in the bottom is the intensity of the beam. The intensity of the beam goes up, down, and then up again to the other side. That's your vortex beam intensity profile. Nice, nothing special. And what we measure is, I showed you, so for each of these points, we measure a curve like that, so a curve like this one. And what we measure is the depth of this curve. So we measure the resonance depth as 1 minus this value divided this value here. So, and that's what we plot here. And what you see is that when they are co-rotating, so when you're insensitive to motion, you move your ion across the beam and you barely see any change. Of course, when you're, as I said, when you're getting close to the center, what happens? Your signal drops to 0, so your errors are a mess, and your signal is very bad, but you still see this maintaining more or less constant. And in the counter-rotating case, where you're supposed to be sensitive to the sinusoid velocity and actually diverging with R, the peak depth goes lower and lower and lower to 0, and then it goes up again to the other side. We tried to fit an analytical data to an analytical model to this data, but it wasn't possible. This is something similar to what we reproduce, but the thing is that the thing has too many parameters, and we could fit stuff to it, but we would just be playing with the parameters. So we decided to do something which was getting rid of a lot of these parameters, because one of the things that actually makes this funny shape of the purple curve go up and down like that, and then here die and so, is the fact that the power is going up and down a lot. Power is going up and down a lot. So we redid this measurement, but maintaining the power constant. So when we went to this point, we would raise the power of the beam to give a given value. So, and for each point, we would either raise or lower the power of the beam so it was constant. So that all of other things maintained equal, we should be having something which is much easier to model. And in fact, this is what you see here. So this is just moving the ion on one direction, so not to the other direction, because it's symmetric, we already know that. And we did this for two different beams. So one beam that had a bigger radius, so this is again the intensity of the beam with a bigger radius and the beam with a smaller radius. And we saw this very surprising thing, which is actually what we were expecting to see, which is independent of the radius, the resonance depth had exactly the same behavior. We could model this behavior very well with what we call the full model, which takes all of what we could think of into account very nicely. But we could also model this very nicely by the Bessel zero function and 1 over r. So this doesn't say 1 over r, but it's the modulation parameter, the Bessel function square. So basically, this behavior that we're seeing here is compatible with a very simple model that the Doppler shift diverges like 1 over r. Of course, it diverges, and near the center, as I said, we cannot measure, because at this point we cannot put power so high up that we actually managed to match that, and that's all okay. But we have this 1 over r behavior, which was a nice thing that we were looking for, that shows like the smoking gun of the effect. So, what do we conclude? Yeah, we unequivocally see the rotational Doppler effect. It has the structural features that we expected, but the next questions that we ask ourselves is, can we reach what we would call the super Doppler limit? That's what we're heading for now in the lab, and actually we're having some promising results this week in the lab, which is can this effect, can this Doppler effect, this radiant Doppler effect, be bigger? And we go back to 1 second. So you see, here you have K, and here you have L over R. At some point, this thing could be bigger than K. There's nothing that limits you in this respect, and that would be what we would call a super Doppler effect, so a super Doppler shift, so a Doppler shift which is bigger than the longitudinal Doppler effect. This effect can also be used to sense temperature, could be in principle used to sense temperature transfers to the beam that's sensing it in the same way I was explaining it here. And the other thing that we have in the future that we would like to see is something that people have come to name super kicks or Berry super kicks, because Michael Berry, the physicist known for the Berry phase, actually proposed this idea, and he basically came to say like, okay, of course, like every sensor is also an actuator, and every actuator is also a sensor, so something that you can use to sense Doppler shift can also use to impart motion of the ion, or the other way around. Almost every physical phenomenon can be looked as a sensor or as an actuator if you look at it carefully. And so we know that in the planar wave we have the longitudinal gradient, as I said, that gives you longitudinal kicks. I showed you in the first experiment how the radial gradient can be used to impart motion in the radial direction, but what about the azimuthal part? So the motion in the radial direction, as you see, scales as the width, so the focus size, so this is limited by how good you can focus a beam, and that's ultimately limited by the Abbe diffraction limit. But in the case of the azimuthal part, you could have a momentum kick, which is not only, so now add this up to these other two terms, with a term that goes like L over rho, which can basically diverge. And because of the size of the wave packet of an atom or an ion, we don't expect it to diverge, but it could be even 4 times bigger than K, which is something that we are on for the hunt to see if we can actually see these big kicks, and we hope that in a couple of years it can happen that we observe it. Good. Closing remarks. So I'm finishing with this last slide of closing remarks on my lecture. So things I want you to probably think about or take home. So first I showed you atoms can be excited in the dark. It's kind of interesting and counterintuitive, but you can excite electronic transitions, motion of electrons, even if you are in a place where what we would call like a dark penumbra. So it's not totally in the dark, but the penumbra of a beam. So structured beams can transfer orbital angular momentum to bound electrons and also to center of mass of whole atoms. And in the end, I showed you how we have seen the footprint or the mirror effect of what we expect to observe in the future, which is a superkick. And so some of the things we would like to, I was asked in different moments during this conference, okay, but what can you use this stuff for? I personally would say I'm more interested in seeing these effects and seeing this beautiful physics, which is sometimes counterintuitive and learning from it. But of course, sometimes you're looking at things on which to apply them, and some of the things that we have looked into and would like to promote its work is like, okay, we were looking into turning ion crystals or using rotational effects on crystals with the structured beams. You can actually think of not only using this Laguerre-Gaussian beams, but especially structured vector beams for what I would call full atomic control. So you can tailor very precisely your interactions and decide whether you want to change your magnetic number or your motional state if you allow yourself not only to have Laguerre-Gaussian beams, but general beams that focus and have a given specific space pattern and polarization at the atom position. And another idea to to explore that. That's what I was telling you a little bit here, which is can you actually do quantum gates between atoms using structured beams. So with that, I will stop talking. I will hope that you ask me some questions, and I will ask you, if you have time and will, come to me and give me your feedback on this course. But if you don't want or feel shy, you can scan this QR, which is a different one than the one before, and just leave a comment on this Google form, just saying, I liked it, I hate it, please change that, please tell me here you have this wrong, whatever. I will be very happy to hear written comments as well as oral comments on the next days that I will be here. Thank you very, very much for your attention. I hope you enjoyed it.
Great, thank you. Questions?
Thank you, Christian. Beautiful, and beautiful work, beautiful course. I really enjoyed it. Maybe I missed something, but in this last experiment, the Doppler shift experiment, you're using CPT basically as a probe, right, of the motion of these ions. But the same beams that you're using to obtain your CPT curve are the beams that are imprinting actually the Doppler shift, or did I get that wrong? Yeah. Is there any reason why you use the same beams for those, or could you use different beams to drive this CPT phenomenon and use that as a probe, or do you need them to be the same beams?
So I would say the CPT phenomenon is affected by the Doppler shift, so it has to be the same beams. So in our experiment, the situation, the laser configuration is a bit complicated because we have this beam that pumps population into these states, and then we observe the resonances between these states. There are some other situations where, with some other atomic species, you actually can observe, also with calcium, you can observe CPT just with this laser on just this transition by between one and the other one. We did this way because it's nice to work with infrared beams and structured beams. Structuring violet beams can be done. We are going into that direction, but it's a little bit more complicated.
More questions?
Thank you again for your presentation. About the ion trapping with the standing waves, I was wondering if the ion scatters the light a little bit, or if that is negligible.
If the ion scatters light,
Yeah.
yeah, it scatters light all the time. So, I don't know how to address this from the beginning, but I will go to show you. I will go to the very beginning. So, what you see here, that little dot there is scattered light by the atom. That is really scattered light. The way these experiments work, go again, is, okay, I don't have the full experiment set up here, but, so the way this experiment works is, you shine laser on the ion, and you collect the scattered light, so this ion scatters light from this laser in one direction, and some part of that is collected in this direction. And here the camera is not there, but the camera is collecting some part of the scattered light. And through that scattered light, you can tell that the ion is there, you can tell the electronic state of the ion, and yeah.
Sorry, I meant the light that you use to trap the ions.
Yeah.
Does the ion scatter that light, and maybe it makes it attenuate?
Oh, we trap our ions with oscillating electromagnetic fields of low frequency. That's the pole trap works with an electromagnetic field, but a very low frequency. It's not light. We're not using optical tweezers to trap, as in the atom case, and so there's no scattering light in that respect. But for example, in experiment, not the reality things that I'm talking to about, like for example in these experiments with atoms, these atoms are trapped with light fields. But what you normally see, so this image here is not the scattered light because of the trapping field, but the scattered light of a resonant laser beam that is being used to observe the atoms in place.
So thank you for the excellent presentation. Maybe it's something you could give me an indication about, not exactly something you were doing, but I was wondering when you showed this last part about like using structured light to this Doppler effect, this azimuthal Doppler effect. If you have considered, for example, if that would have some influence when you're doing nonlinear processes in an atomic gas, like a third order nonlinear process, because you also have like two beams you could structure. You're doing, for example, four-way mixing or something like this in an atomic gas or something like this. Do you think this Doppler effect would be relevant? Or, I don't know if you have any insights about that.
Yes. Sorry. I'm doing a slow answer, but yeah, the answer is yes, actually. And this experiment here, which inspired us, was done on a hot gas vapor cell and seeing four-way mixing with structured light beams. The bigger difference was called spectroscopic observation of the rotational Doppler effect. So they saw spectroscopic evidence that there was a rotational Doppler effect, but as they were working with a dilute gas in a hot vapor cell, they had no way of saying how the Doppler effect depends on the position of the beam. So they saw evidence that spectroscopically what they were seeing in a four-way mixing experiment had shifts and line shapes that were changed by the rotational Doppler effect. But as the gas is a dilute gas, you have no spatial information. The nice thing about this reversion of the experiment that we did, I forgot to put the year here, but it's almost 20 years afterwards. This is an experiment from yeah, here it is. Yeah, 18 years afterwards, is that we have, as you see here, the spatial resolution. We can move the ion through the loop.
We can have a final question if there's any. If not, let's thank Christian for a great